And the last talk today is Joseph Hua, who's going to tell us about the Ax-Grothendieck theorem. Over to you.
Hello. Yeah, the Ax-Grothendieck theorem is a model theory result that people always sort of point to when they're like, model theory can be used in algebra. And this is what it is. It says any injective polynomial map over C is surjective. So a polynomial map is a map from Cn to Cn whose each n component is a polynomial in n variables. So this generalizes the statement about injective linear maps from Cn to Cn. Yeah. And the proof is basically applying the Lefschetz principle and reducing the problem to Ax-Grothendieck for locally finite fields. I'll tell you what these things are. So this part of the proof, Ax-Grothendieck for locally finite fields, doesn't use model theory. So I won't be focusing on that. I'll be focusing on the Lefschetz principle, which is the model theory. So locally finite field is one of the equivalent K. So K is locally finite. Field K is locally finite if and only if it is an algebraic extension of a finite field. If and only if any finite subset of it is contained in a finite subfield. If and only if it embeds into the algebraic closure. The first and the third are basically a property of the algebraic closure. And the Lefschetz principle is it's about things being true for algebraically closed fields of characteristic 0. So by a property here, I mean a sentence in model theory. So you can take it as like a proposition about rings. Basically, it's a property about rings, if you like. So property phi about rings is true for C, if and only if it is true for all algebraically closed fields of characteristic 0. And this is packaged in model theoretic term. The theory of algebraically closed fields of characteristic 0 is complete. If it's true for one model of the theory, then it's true for all the models of the theory. That's the first part of it, which was I think this was the first part that was conjectured, and it's what people used to justify doing algebraic geometry over any field of characteristic 0, I think. And then this got extended to this is if and only if all algebraically closed fields with so if and only if phi is true for algebraically closed field with large enough characteristic, as it were, which is quite strange. It's like it's saying C behaves in exactly the same way as a big enough characteristic algebraically closed fields. And going between these is using the compactness theorem, whose slogan pretty much proofs only have finite linear hypotheses. Also abbreviates to proofs are finite, which I think is a bit inaccurate because it's more about the hypothesis. So this is going to be my project. I am almost here, or sort of halfway there. So this lemma is a transcendence degree and characteristic to determine algebraically closed fields up to isomorphism. This is the key lemma to show that theory of algebraically closed fields of any characteristic, of a certain characteristic, is complete. The other side, compactness, has already been done in the Flypitch project, which was a thing in Lean from like a couple of years ago, I think. And I'm working off their definitions for basic model theory stuff. So that's where I am now. And so far, in getting there, I have shown, actually, yeah, I've shown along the way that commutative rings are the same things as model of the theory of commutative rings, and same with fields, and half of the direction for one direction for algebraically closed fields. And yeah, I've defined transcendence degree, and I've shown some basic things about transcendence degree, and I've sort of laid the structure for this result, but I haven't finished it yet. As you can see, there's a lot more to do. I think I'm basically going to spend the rest of the time talking about this. This is I thought this was quite cool. It was correspondence between structures in the model theoretic sense and structures in Lean. So in model theory, you start out with a language, which for our purposes is just a bunch of function symbols. And for rings specifically, these function symbols will be 0, 1, minus, plus, times. Each have their own arity, 0 and 1 arity 0, minus is arity 1, and plus and times arity 2. And in Lean, well, these are just function instances, has 0, has 1, has add, etc. So there's a little bit of discrepancy between this and this, which I will talk about in a bit, and that's there's not really a mention of A in model theory. So where is A being a structure in the language of rings means has 0A, has 1A, has neg A, has add A, has mol A. Pretty much, it corresponds to that. In the model, the way to say it in model theory is you can interpret the function symbols in A from the language. So this is entirely in the theory, whereas this is with the mention of a structure. So here, back to the theory. Given a language, you can have terms in the language, which is basically anything that you can build using the function symbols and a bunch of variables. So for rings, these will sort of be pre-polynomials, in the sense that pre-polynomials in n variables over z. And that I don't say polynomials because you don't have like x0 plus 1 is equal to 1 plus x0. You don't have commutativity and things like that, because they're just symbols at this point, until you interpret them into the structure of A. Maybe they'll have A will have those properties. So yeah, basically think polynomials, but you don't have the things that polynomials tend to satisfy. Yeah, and on the type theory side, these are really just terms that you can build in the context of these variables. So once you have terms, you want to make properties about rings, and basically, so these are called sentences. Basically, all you can do is stick equality between terms and put logical connectors and or not, and then you also have to bound all the variables. So for all the system from, and these correspond to predicates in A. Here is what you imagine commutativity to be expressed as, and obviously on the Lean side will be more common. For the then you have like theories, which are sets of sentences, and the theory of commutative ring. Well, you know what they are. It's like associativity and commutativity of addition, etc. And this is all packaged together in one structure / instance, common ring A, or class, I mean. And A being a model of rings, so A is already a ring structure, and A being a model of the theory of rings also is com ring A. And this is the important point about model theory, because it distinguishes between models of the theory that they model from it distinguishes models from the theory, essentially. Whereas in algebra, when we try and prove stuff about theory, we tend to work with a generic model. Like we let A be a ring and we show stuff about A, but we don't. You sort of don't need that for logic. And in that vein, model theory allows us to manipulate the sentences themselves instead of, as well as manipulate the algebraic objects. So, like, for example, you can have a set of sentences about rings, whereas that doesn't, so you don't have access to that in the conventional way of doing algebra. And yeah, that's all I have to say, really. Thank you.